And Autumn, the floor is yours.
Great. Well, first of all, I just want to say we really appreciate the opportunity to speak to you guys today. I'm going to be talking about how to use fluorescent dye tracing to support groundwater investigations in karst environments. So let me get my screen up. Great. Okay. So for a little context, I'm going to give a very brief description of some of the principles of dye tracing as we use them in groundwater investigations, and then move on to some more specific examples. So although the science of dye tracing seems pretty straightforward, it can be a bit complicated in terms of the details, but it is a relatively simple and inexpensive way to derive a lot of great information about the velocity and direction of groundwater movement. This can establish point-to-point connections from surface features, which would be your injection locations, to groundwater resurgence points. And this is useful because we know that the extent of groundwater basins cannot always be delineated from surface topography alone. We know that subsurface flow paths and travel times vary because karst systems are so heterogeneous and anisotropic. And so using dye tracers as models for flow can really provide some excellent information to then further inform your groundwater study. This is just a familiar block diagram that is representative of the karst environment we have here in Kentucky. And we often discuss groundwater in the context of karst here because this type of geologic environment is so prevalent. The extensive karst development results in increased groundwater vulnerability due to the rapid infiltration and relative lack of filtering of runoff as it moves from the surface into the karst aquifer system through direct through direct sources like cave streams, cave entrances, sinking streams, blue holes, things of that nature. We also know that solutional features in limestone enable the communication of groundwater between basins, as I said earlier, that would be considered discrete based on surface topography alone, and that the secondary porosity contributed by these large and sometimes extensive cave passages enable contaminants that enter the aquifer to be transported at great distances rather quickly. So with tracer studies, we can both understand the groundwater movement and model the transport behavior of dissolved constituents in the groundwater. These properties make fluorescent tracers useful in a broad number of environmental applications, including mitigation, source water protection, basin delineation, monitoring the efficacy of existing groundwater monitoring systems on industrial sites, and really any application where you need to connect a point on the surface to the subsurface drainage and ultimately to the resurgence location at a spring or a base level stream. As I said before, this is simple in theory. Tracer is introduced at point A and is recovered at point B, so we can say points A and B are hydrologically connected. There are a few things that you want to consider to ensure that you have a successful trace. And the main ones I've listed here. Of course, there are lots of other details that I'm happy to talk to you guys about in the question session. But the first thing that we do is conduct a thorough hydrologic inventory. So we want to catalog all the springs, seeps, seeking streams, sinkholes, surface depressions, caves, cave streams, anything that is a source of communication between surface flow and the aquifer system. And we usually do that in a 360-degree radius from your study area. Now, if you have other information, say, potentiometric surface data that tells you, groundwater is unlikely to move in a given direction, then you may be able to refine your hydrologic inventory. But it is a good practice, to spend the time to do this, because your main goal is to recover the dye. And if you don't do that, then you cannot confirm or exclude hydrologic connection between any of these points. So definitely spend the time to go out in the field, ground truth what you're seeing in your desktop review, so that you can be sure that you are identifying not only monitoring locations, but also potential injection locations. As far as injection locations are concerned, you want to opt for something that shows evidence of a more direct connection to the groundwater. So you would be looking for characteristics like high acceptance rates at wells, or surface depressions and open sinkholes, or maybe you would look for soft or sunken soil, or even channelization towards a feature where you can tell that water is draining towards that location and then disappearing in the subsurface, which is what we see so commonly in karst environments, because we really have a great lack of surface drainage due to that prevalence of soluble bedrock near the surface. So choosing the right injection point is going to ensure that your tracer does enter the groundwater system and does its job. You can affect the rate on that if you choose to prime or flush your injection location, which is something that we always recommend. It's part of our standard practice. And so typically we introduce about 1,000 gallons of prime water into a feature before introducing the dye, and then we flush it with at least 1,000 gallons as well. Now, depending on your injection feature, that can take a few minutes or several days. And so you do have to plan for that. We always do capacity testing and check out the acceptance rates prior to selecting an injection location, and kind of help that plan for our timing as well. Next, you're going to want to establish background fluorescence at your monitoring sites. So presence of background doesn't necessarily exclude a given dye from use in a trace, but we would want to adjust the dosing accordingly so that we can overcome the background. And then once we have baseline fluorescence, we can select the type and amount of tracer that we need to use on a project. This is going to involve review of any existing background and also the hydrogeologic characteristics of the injection and monitoring points. Some dyes we find work really well in turbulent flows over short distances, and other dyes perform very well even in diffuse flow over great distances. Okay, so moving on to some specific examples of how we've used this. The first example is talking about how mitigation efforts were supported to remediate contaminated karst groundwater in Tennessee. The Tennessee Department of Environmental Conservation contacted us after they found evidence of petroleum contamination. That they were alerted to that by reports from local community members and residents who reported strong odors emanating from water at the surface that was in residential yards as well as in some public spaces. And so TDEC compiled a list of potential sources based on current and inactive underground storage tank facilities in the area. So here we had an urban setting with all the associated urban features to consider, stormwater drains, utility lines. There was significant rerouting of natural surface flow, and all of these things can impact groundwater movement in the area and make it a little bit more difficult for us to understand what's going on. In terms of the geologic setting, this was Ordovician shales and carbonates, primarily limestones, right in this region here. And so since primary permeability in these units is fairly low, groundwater movement occurs mostly along secondary solutional openings and along the bedding planes, joints, and fractures. So here are some examples of the properties that were impacted by this hydrocarbon contamination. You can see down here in the bottom right, this is one of the residences, and the fumes were so strong here that as we would drive down the street, if the windows were down, we were experiencing, almost instantaneous acute physical symptoms like headache and nausea. So it is quite incredible to think that the people who were living here were dealing with this on a day in, day out basis. And that was part of the motivation to really try to find a expedient and thorough solution to this issue, because human health and safety was at risk here. Quite simply, the objective was to determine whether groundwater flow from any of these potential source locations was in fact traveling to the impacted locations, and this would inform both operator responsibility as well as focusing any remediation efforts. So this project took place in 2 phases. In phase 1, we worked with the Tennessee Department of Environmental Conservation to identify 2 underground storage tank facilities that would be traced as potential sources. We used unique tracers introduced into monitoring wells at each location, which exhibited the highest acceptance rates. Again, that suggests a more direct connection to the aquifer, which is what we'd like to see. In terms of outcomes, the phase 1 tracer results did indicate a hydrologic connection from the Gallatin Market in Delhi to the impacted seeps here along this base level stream called Town Creek. We had a travel time of about 6 days post-injection, so approximately 250 meters a day. The second injection was performed at a facility just about a block away, and it took 19 days to recover that dye, and we found that it was actually moving in the direction of the southwest, away from the impacted seeps. As I said, that was 19 days post-injection, minimum travel time of 44 meters a day. The second phase focused on identifying optimum locations for introducing remediation materials, and also testing whether the presence of a shallower flow regime could expand the list of potential responsible parties here. It was proposed that if there was an upper flow regime that existed at the Petro Plus or some of these other operators in the area, that the dye introduced in the first round of tracing may have been below the elevation where that upper aquifer exists. And so to test this, we grouted the wells above the injection where the location where the original injection took place, and identified intervals about 540 to 540 feet above sea level. We grouted those to effectively close off communication with the lower aquifer, and then injected the tracers. And you can see those results here. Again, the phase 2 results excluded the Eocene trace here at Petro Plus as a potential source, but we did identify an additional facility over here shown at the purple injection location. That was the L&R Market, and it also exhibited groundwater movement northwest in the direction of the impacted seeps. We did continue to recover the rhodamine WT that we injected in the 2019 traces, further establishing, the connection of these 2 operators to these impacted locations. I will note that these are inferred flow paths. The exact flow path to each monitoring point, as well as exact locations of bifurcation, are not known. And this is where some of the geophysical work that was involved in this project really came in. We were also testing where we could most effectively introduce remediation material. We found that an upgradient well that was actually a little bit further away from some other ones that we tested did exhibit a direct connection to these impacted seeps, and within 4 days of injection we were recovering it. So that made a very good candidate for introducing the BOSS trap and treat hydrocarbon remediation technology. I will note that we did not recover the tinapal that was injected into this closer well. There are several reasons that that could have happened. Notably, tinapal does best in turbulent flows, and so although this was a short distance, it was into a monitoring well. We were hoping to hit an elevation where there was a preferred flow path, which would take the short distance that it needed to go to these impacted seeps, but we were not successful in that effort. So this turned out to have a pretty happy ending. The issues at the residential properties were resolved, and I'll show you guys some examples of that in the next slide. There was interpretive signage placed along the Greenways Trail near some of the impacted sinks. And so this educated the community about the vulnerability of karst environments and karst groundwater to contamination, and it also provided a record of the remediation efforts. And finally, the BOSS trap and treat hydrocarbon remediation material was injected into IP20, and that remediation is still underway. And so here you can see some of the photos at the top. Before, you can see the staining. They dewatered and excavated the site, put in a French drain, and piped that out here to a nearby ditch, and then ultimately cemented and built over the seep in this person's backyard. And so we were really pleased with those outcomes. Oh, jumped ahead. And yeah, that's about it for this particular one at the Town Creek Greenway. We've also used fluorescent dye tracing to support dam safety and dam risk assessments in karst. We know that dams that are constructed on karst foundations are at an elevated risk for failure. Patoka Dam in southern Indiana represents one case where karst processes were thought to be impacting the integrity and the overall safety of the dam, which had recently received an elevated risk assessment. In response to that, the U.S. Army Corps of Engineers contracted us to conduct a groundwater flow investigation in that vicinity to evaluate the efficacy of the water control structures. Defects including structural weaknesses caused by the undermining of unconsolidated materials as the water is moving through them can cause structural weaknesses in the dam. These result in difficulty or inability to maintain pool stage, which of course could be problematic for navigational waters or recreation or drinking water reservoirs. And of course, dam failure could result in catastrophic flooding, damage to other infrastructure, and hazards to human health and safety. This is an aerial view of the area. We have the main dam here, as well as some grout curtains and the abutments along the side. And here in the spillway, a concrete cutoff wall, and then some more grout curtain extending over to the dike region. Now, water leakage, as far as a water storage standpoint, was not the main concern here. Again, we were concerned with identifying any potential seepage pathways that could lead to internal erosion of the unconsolidated dam materials. The objective here, again, evaluate the function and geometry of this karst network that could affect the integrity of the dam structure. We conducted a groundwater flow investigation using fluorescent tracers. We also paired this with an analysis of the water table elevations and spring hydrographs. Since the groundwater and sediment flowing through the conduit system led to a relatively large spring just downstream of the dam, known as Robert Hall Cave Spring, that could potentially be impacting the integrity of the water control structures associated with this dam, we undertook an effort to delineate the recharge basin of Robert Hall Cave Spring. And this was very instrumental in better informing our assessment. So the dye tracing results, oh, sorry, my lights went out. The dye tracing results identified local flow south to north, moving toward Robert Hall Cave Spring, right here. The mean travel time was about 2 to 3 meters per hour. But the results also indicated that groundwater was in fact bypassing water control structures in the vicinity of the cutoff wall in this region, but the geometry of these flow paths was not exactly known. So the dye tracing results in combination with the potentiometric surface data and isopack mapping indicated that the recharge area of Robert Hall Cave Spring approximately corresponded to the extent of the Glendine limestone outcrop shown here in this isopack map on the left. And then you can see on the right, our groundwater basin supporting Robert Hall Cave Spring does follow that rather nicely, as might be expected. So ultimately, the study informed our choice of target areas for more intrusive and expensive investigations, such as the installation of monitoring wells and borings along the dam and abutments. And this allowed the U.S. Army Corps of Engineers to prioritize target areas for additional investigation, not only saving time and money, but ultimately providing better risk assessments and dam safety management in the future. This can then reduce the risk of catastrophic failure, saving lives, and of course, preventing loss of huge financial sums and allowing the dam to continue to serve as a flood control mechanism as well as recreational and stimulus to the local economy. Ultimately, they did downgrade the probability of failure for this dam. So that was another win. And lastly, in the few minutes I have left, I would like to talk about the groundwater hazard map that was created for the Mammoth Cave biosphere region. Perhaps some of you, if you're familiar with Kentucky, know that we are home to Mammoth Cave, which is the longest mapped cave in the world currently. And it just so happens that there are some major transportation corridors that pass through the recharge basin of Mammoth Cave. And previous spills along this corridor did pose a threat to the groundwater quality as well as the sensitive aquatic biota therein. The development of the groundwater hazard map was motivated rather by massive releases of fuel that went directly onto the ground surface. Because this was in a very karstified environment, the lost fuel rapidly infiltrated the ground surface through that shallow soluble limestone layer and was never recovered. And so in response to that, the Mammoth Cave biosphere region got together with CHL, State of Kentucky, and the Department of Transportation to help create a groundwater hazard map that would then inform future spills on how those can best be handled and hopefully mitigate the effects of future releases on water quality to the subsurface. So in this picture, you can see there are some new drains that were installed as a result of this, as well as some of what they were trying to extract. And then I have some examples of the cave shrimp and cave salamander that are found within Mammoth Cave. Both are protected species. And so that was part of the concern in trying to create a better highway management system, a better transportation system to avoid introduction of anything spilled along that into the groundwater. Here you can see an example of the product. This is just one page of many, but this happens to be along a major exchange on the interstate that actually leads into Mammoth Cave National Park. The dashed lines that you can see there represent known or inferred drainage basins. And we also have marked Class 5 injection wells, which here in Kentucky, that is essentially a open sinkhole that can accept water from the surface into the subsurface. We've also got injection wells, sinkholes, soil collapses marked here, and many of those served as injection locations for the traces that informed this study. The dye tracing results did show surface drainage along the interstate and the CSX railroad moving in the north direction towards Mammoth Cave National Park and ultimately emerging at springs along the Green River. So in terms of outcomes, we were successful in defining local drainage basin boundaries. We also established groundwater flow direction and minimum travel time for contaminants released along these transportation corridors to reach the cave assets at Mammoth Cave National Park. It also informed roadway engineering practices and was eventually adopted by the Kentucky Transportation Cabinet as the Karst policy, which applies to all roadways and karst areas across the state of Kentucky. So this has been pretty impactful. And over here on the right, you can see some of those engineering practices having to do with retention basins and plantings to absorb water, as well as swales below to help slow the infiltration of that water. We are still dye tracing at Mammoth Cave. The extensive nature of this karst system, combined with the need for more infrastructure like sanitary sewers and parking lots, results in an ongoing effort to understand and protect the subsurface drainage and the rich resources that it protects. Once contaminants enter the system, extraction and recovery become very difficult, if not impossible, due to the sheer scale of these caves. And so in instances like this, mitigating effects often involves prevention of contamination to begin with. And so the groundwater hazard map is just one way that we've been able to do that. So with that, I'm going to thank you for your time today. I do appreciate the opportunity to share some examples of how we apply dye tracing in natural settings. There are numerous other applications, of course, both in natural and industrial settings. If you're curious about how dye tracing could be applied to your project and are interested in any of the techniques that we use here at CHL, please don't hesitate to reach out. Our contact is here on this slide. And with that, I will turn it over to Sophie.
Thank you very much, Autumn. So for the participants, if you have questions, don't hesitate. There's already a very nice message for you in the chat box. And also a question from Sarah Lily. She asks, she's curious about the priming and flushing processes before and after tracing and injection, and how does this influence groundwater felicity estimates?
It is true that if you're wanting to do a quantitative trace and you're looking to recover a specific dye mass, or you're wanting to determine a specific velocity, priming and flushing can increase that velocity, right? Because you're putting hydraulic head into the system, and so that would increase the velocity. I would say, this type of tracing is best used for velocity measurements in highly karstified areas where you may not need to flush or prime. Could be very useful in like cave stream environments where you have an active water source, and so injecting the dye into it is very simple, and then you can get point-to-point velocities. If you are concerned about how it will affect velocity in, say, a well trace or some situation where you are going to have to use priming and flushing, I would recommend testing that beforehand and doing your calculations and then introducing your tracer.
Thank you. If there are other questions, don't hesitate to mention them either in the chat or by raising your hand in the reactions and ask them directly. I do have a question actually, Autumn, for you.
Yep.
in your first example about the hydrocarbon pollution, you mentioned that you inject how many gallons of tracer? It sounded like a lot. So I was curious about that.
I don't think I included that information. It was not a lot. I think the most we used was 2 gallons. So for this particular trace and the distance, that is kind of a lot. As I said in the first trace, we continued to recover that dye 2 years afterwards. So we were looking to establish direct connection, and so in that case, we erred on the side of caution and dosed a little higher. But typically for us in karst environments, 1 to 2 gallons, 1 to 2 pounds, we mix it a 1-to-1 ratio, is sufficient. But of course, it does depend on the characteristics of the location itself.
And how do you recover the dye afterwards? What technology do you use?
Oh, thank you for asking. So we use both water sampling and charcoal sampling, which I think is a little different from what some other folks may use. We really like the charcoal sampling. I can kind of show you an example of what that looks like. So we just have little mesh bags filled with activated coconut charcoal. And so these are passive receptors. We deploy them in the water. We use those to collect initial background, and then we also use them in our post-injection sampling. And so for the duration of the time that these are deployed at a monitoring location, any dye that's in the water will be accumulating on them. So it's a little different from water sampling in that you have a cumulative sample versus an instantaneous moment in time. But we find that it is very useful if you are using remote sites where access might be difficult, and you might not be able to get, say, an automatic sampler down, or you don't want to camp out and just take a bunch of water samples until your dye comes through. So we use both, but primarily charcoal.
Another question from Sarah Levy. She asks if most standard dyes have concentrations of 20% or something else?
It really varies. We have dyes from 20% up to, I think, 86 in terms of purity. And then we mix everything at a 1-to-1 ratio as far as mass dye to volume of water.
Any other questions from the participants? I will, if that's okay for you, I will leave your email address in the chat box so people can contact you if they have other questions that pop up later on.
Yes, absolutely.
Okay. Well, thank you very much. And I think Pierre Jamin can start sharing his presentation.
Yeah. Let's share my screen. Okay. Do you now see the slides?
Yes, we can see your slides. Thank you.
Thank you. So thank you, Sophie and Aqua, for this opportunity to present our work. The purpose of Nagare is to bring more scientific relevance and economic efficiency in the management of polluted aquifers. So in risk management, and this of course also applies to risks related to aquifer pollutions, uncertainty is expensive. So of the average budget for environmental management of polluted sites, 15% is spent on the characterization of the pollution, and the remaining 85% of the costs are actually the cleanup cost or the remediation costs. So what we propose is to increase a bit the share of the characterization studies to better understand what happened in the aquifer by, of course, using our services in order to reduce the risk mitigation cost that can be monitoring plan or remediation plan up to 30 and sometimes more percent. So how do we achieve this? As I said, by being more relevant. So currently, when we have to characterize a polluted aquifer, we analyze the concentration of pollutants found in the water. So to know if there is a lot or not much. So then these concentration results are compared to standard or threshold or quality concentration values that come from the legislation or from guidelines or whatever. And they are used, of course, as decision criteria. So in this case of a really simplified aquifer with 2 layers, we can see that there is a lot of pollutants in the bottom layer and not much in the top layer. So we will logically focus the effort to treat the lower layer first, of course, to avoid all this pollutant ending up in the groundwater abstraction well drawn in the right-hand side of the picture. And the thing is, we could be wrong, actually, because if we consider solely the concentrations, we forget to quantify precisely what causes the pollutant to migrate in the aquifers, namely the groundwater flow or the groundwater flux or the Darcy flux. Because in this case, there may be less pollutant in the upper part of the aquifer, on the top of the aquifer, but these pollutants are carried to our catchment much more quickly by the groundwater flow. So it's actually the upper layer that's the most problematic. And this is exactly what we do. Our technology allows for a direct measurement of groundwater flow and a calculation of pollutant mass flux at existing wells. We are also able to monitor this flow in real time to capture the temporal dynamics of the groundwater fluxes. And we also have remote data transmission, so we can, of course, do a distance monitoring of the groundwater fluxes. So before explaining what's our technology, I have to define some terms that I will use. So the contaminant mass flux measurement require simultaneous measurement of first the contaminant concentration or the solute concentration in the water and the groundwater flux or Darcy flux. The multiplication of the two give actually the mass flux, what we call the pollutant or the solute mass flux that is moving through a unitary flow area of the aquifer by unit of time. And if now we integrate the contaminant mass flux on the area that is representative of the plume, we end up with a mass discharge. And this mass discharge is actually the amount of contaminant moving through this control plane by unit of time. So for example, if, let's say, benzene is the pollutant of concern, we can say at a precise location of the benzene plume that we have actually 5 grams per day of benzene moving at that location. So as I said, we need two simultaneous measurements, the solute concentration and the Darcy flux. The contaminant concentration is already often measured by the consulting company on the polluted side, so we already have access to the data. So we focus on performing the groundwater measurement. And this measurement, it is done by a single well tracer dilution test. So this test requires a continuous mixing of the water column in the well to ensure an even distribution of the tracer mass. A tracer, of course, that is injected at a low and constant flow rate in the piezometer, and a continuous monitoring of the tracer concentration within the well. The tracer can be a salt tracer or a fluorescent dye tracer, according to hydrochemical context. And of course, we know, of course, the mass balance equation that governs this this process, and we can calculate the groundwater flux that crosses the screen of this well and carries the tracer out of the well. So at the measurement of a steady state groundwater flow by our technology gives this typical evolution of the tracer in the well. So of course, at the beginning of the experiment, you don't have any tracer in the well. And you start the tracer injection, so the concentration of the tracer in the well rises until a certain time where it reaches an equilibrium between the tracer that you inject in the well and the tracer that is flushed out of the well by the groundwater flux in the aquifer. So this stabilized concentration is compared to the injected concentration, and it allows the calculation of a dilution which is proportional to the groundwater flux. So of course, if we have a high groundwater flux, the dilution will be high because we have a lot of water flushing our tracer out of the well. And of course, we will have a stabilized tracer concentration that is really low. Okay. So this measurement is valid as long as the groundwater flux is constant in the aquifer, so in steady state. But of course, nature is not steady state. And now, what if the flow varies in the aquifer because of any transient processes? So practically, as long as I have tracer to inject in the well, I can maintain the groundwater flux measurement. So when the groundwater flux in the aquifer increases, the dilution of the tracer in the well also increases. And of course, the measuring concentration drops. So if the groundwater then slows down, the dilution of the tracer will be, of course, will decrease actually, and the concentration will rise. And so this allows us to perform real-time monitoring of transient groundwater fluxes. And it can be very useful in various contexts, such as if you have an aquifer that is related to surface water, or even to the seawater, where you have tides that interact with the aquifer and can really influence the dynamics of the groundwater flow. So our connection to TrackWise is, of course, through the use of the stream fluorometer. We use it as a part of our setup to measure the fluorescent dye tracer concentration. It is quite useful for us because it's really compact. The probe is really compact for its size. It doesn't require any external power supply. And also because it's compared to other commercially available probes, it's really robust regarding the influence of turbidity or the influence of variation of temperature. And but in our view, it can be maybe improved by adding some kind of connectivity that can be, let's say, for the probe to be integrated in a more complex data acquisition system. But it's really a nice device. So as Sophie said, actually, I developed this groundwater flux measurement technology during my PhD in the University of Liège in Belgium. And currently we are financially supported by the Wallon region of Belgium. And we were able to build 2 compact modules and a kind of mobile monitoring unit on the trailer for us to measure and monitor groundwater flow. And we are already operational, and we have the ambition to create the spin-off company in March of next year. So when I say us, of course, I will be involved in the company, and also my partner Maxime will be in charge of the business development. And but even if we are still in a project and under the university, we already worked on a series of cases in Belgium and abroad, of course, within the framework of scientific research, but also for environmental consulting company and industrials. And we offer a service that includes the dimensioning of the test that will be carried out according to the problem to solve, and the realization of the measurement on site. And we also work in close collaboration with the consulting company that are usually in charge of the environmental management of a polluted site to better integrate the flux data in the management plan. So now what better illustration than a real case. And this case we actually addressed it last year. We worked on a contaminated site, which was polluted with heavy metals. And the pollution actually threatens the quality of a nearby river. And since the risk at that site is not properly assessed, the regulator imposes a very strict monitoring plan that includes 43 piezometers that have to be sampled twice a year and for another 21 years. So it's quite heavy also financially for the industrial to keep this monitoring plan on. And when we saw this, we immediately thought that we can really bring a value to through our technology to this case. So first of all, we measured the groundwater fluxes at each of the 43 piezometer or 43 monitoring wells. We interpolate these measurements on a control plane, and we could identify that the groundwater fluxes were quite high at 2 points around the monitoring well P5 and around the monitoring well P10. We did the same interpolation with heavy metal concentration data to see that the heavy metals are more present around P7 and P8, located roughly in the center of the control plane. And then, as I explained, we multiply the two, so the concentration and the dorsiflux, to obtain the metal fluxes or the metal mass discharge. And now we can see that we have two really important discharge points of metal. Of course, mainly located around P7 and P8, because that was the location where we have the highest concentrations, but also close to P5 due to the combination of moderate concentration but high groundwater fluxes. Since we have now the mass discharge, the total mass discharge, we can add the mass discharge to have really the total amount of metal that is discharging to this through this control plane. And in this case, for example, I don't remember exactly which metal it was. I think it was for cadmium, this case. But we had a total mass discharge of 5.3 grams per day. And yeah, at this point, usually when we work with an environmental consulting company, the consulting company often look a bit skeptical. And this is justified because there are no threshold values in the legislation or in the law or in the guidelines that are expressed in a mass discharge unit. So they cannot relate this total mass discharge to an actual risk. But for that, we have a trick, and it is a scientifically correct trick. Since we have the groundwater fluxes, we can calculate a total groundwater discharge to this control plane. And we can divide the total cadmium mass discharge by the total groundwater discharge. And in that case, we end up with what we call a representative average concentration. And this concentration is actually the mean or the average concentration that integrates the whole metal discharge through this control plane. And in this case, actually, the average concentration were lower than the threshold value that are expressed in concentration, of course. And it was lower for 5 out of the 8 potentially problematic metals. So for these 4 metals, there were no risk of dispersion by the groundwater. But sometimes, of course, the representative average concentration is not lower than the threshold value, and we have to evaluate the risk for the receptor. And of course, in this case, the receptor is the river. And actually, the mass discharge allowed us to calculate the concentration of metal in the river resulting of the metal discharge. It is actually a simple mass balance, but actually this calculation is enabled by the mass discharge data. And using this, it was possible to claim that there will be no significant impact for another 3 metals on the river. So at this point, out of the 8 potentially impacting heavy metals, only 1 can pose a threat to the river. So we had to keep the monitoring plan on. That was the bad news. But the good news was that we were able to optimize this monitoring plan. And since we know the main discharge point, we can target this area in the monitoring point. So what we can do is we can draw a line. And this line is actually the cumulative contribution to the mass discharge. And it can tell actually that if you want to monitor 80% of the total mass discharge, you only have to keep an eye on 25% of the control plane. Now, if you want to monitor only a bit more, like for example, 95% of the total mass discharge, you have to keep an eye on 45% of the control plane. And this will include this and this and these monitoring wells. And then the consulting company can evaluate the associated cost and maybe negotiate with the industrial or with the regulators to see if it's relevant or not to, for example, double the cost for a few more % of mass discharge monitoring. So all in all, our technology allows us to decrease the number of monitoring wells for this monitoring plan from 43 to 18 wells, and also the duration of the monitoring from 21 years to 9 years. And this resulted in, of course, economic gains for the industrials. But of course, gains, I spoke about the gains for the industrial, but we have to provide also gain for the environmental consulting company and for the regulators, of course, mainly because we can now better assess the risk and better define the risks, or normally everybody is quite happy for that, except the regulators. And also, for example, for the regulators, up to now, the administration also asks if the pollution is aggravating through time or not. And what they did prior to our study is they look at concentration time series at the monitoring wells. So as I said, it's 43 wells times 8 metals. It gives 340 time series to evaluate. So it's quite difficult to define a trend analysis on that. But thanks to the mass discharge calculation, we were able to provide a single mass discharge time series for each metal. So it was much more robust data to perform trend analysis. So the administration were quite happy to have now only 8 graphs to look at and not a few hundreds of graphs. So this was an application for a polluted site. We can also provide, of course, other data. For example, the other application of flux measurement can be for the quantification of pollutant degradation. Because if you look only at concentration, if you look at the concentration downstream or down gradient of a plume, you can have the concentration decreasing. But this is not always a sign of degradation. It can be only dilution. And so the total mass discharge will be the same, actually. But if you do mass discharge measurement, here I draw a little picture with 2 control planes that are located along the path of a pollutant plume. If you have 5 kilograms per day of total mass discharge up gradient and 0.5 kilogram per day at the down gradient control plane, you can really claim that you have a degradation because you really have a mass reduction of the pollutant. So actually, there are lots of other applications, for example, as a source term for modeling, because you can better constrain your model with flux data rather than just groundwater head data. You can calculate discharge to surface water. I already mentioned that. Quantify the natural attenuation. You can also use it to quantify the efficiency of treatment systems. For example, we did a case with an impermeable barrier, and we performed flux measurement prior and after the installation of the barrier to verify that the groundwater fluxes were properly lowered. You can also use it to design remediation system, to, of course, do risk assessment. You can also use it for a complex site where you have multiple sources, because you can add mass discharge. You cannot add concentration, but you can add mass discharge. And so, of course, there is a lot of other application. So whether you're involved in managing contaminated aquifer or dealing with geotechnical project, or more generally in hydrogeology, keep moving forward and think flux. So thank you, Sophie, for the opportunity to present.
Thank you very much, Pierre. So again, if there are questions about Nagare or flux, don't hesitate to ask them in a chat or by raising your hand in reactions. So far, there don't seem to be any questions.
Of course, we are still available through our website, and that is nagare.tech, and also via email, of course.
Okay, can I share your email in the chat box?
Of course, yeah.
So if there would be questions afterwards, don't hesitate to contact Pierre immediately via email. I will share it in a chat box as well. I do have a question, but it's maybe more regulatory.
Yeah.
Because you kind of calculate an average concentrations for the pollutants, but of course at some sites the concentration it's a lot higher than on other sites. Doesn't it? So if the average is below a certain threshold, this is enough for the governmental bodies to accept that there's no more need for monitoring?
Yes, of course. It really depends on the risk assessment. In that case, actually, the risk was for the river, and actually the administration accepted that we have, of course, some point of higher mass discharge, but actually this is diluted by the groundwater that also discharge from the rest of the site, and this water is not contaminated. So it actually the effect of that is a kind of dilution. And of course, our objective here was to say, okay, we have some specific discharge point, but if you consider the site as a whole, actually it doesn't pose a threat because it's diluted by pressure or cleaner water coming laterally in the control plane.
Because in that case, you really have to be sure that you consider the whole contaminated site and that you don't leave out any other sites. Otherwise, your average will be.
Of course, this was of course the discharge because along that river you have other sites. So this is not the only site that can contribute to the degradation of the quality of the river. So actually, you take a lot of assumption and hypotheses to be sure and consider like worst case scenarios. And if the worst case are okay, then the administration is okay. So
thank you very much, Pierre. Very interesting. I think now. Oh, there's one question. I'm sorry, from Mingye. He asks if the method is sensitive to groundwater velocity.
Yeah, that's it. So the groundwater flux is it's what we measure. It's actually Darcy flux. So it's really sensitive to groundwater velocity. So if it's in steady state, of course, we can do like a measurement of the groundwater velocity, and if the groundwater flux or the velocity is changing over time, we can also see it. And for example, we have a monitoring setup that is actually running and since March. So it was 6 months of continuous monitoring in an aquifer that is subjected to tides. So it is close to the sea, and at that location, we can really see the influence of the tide. And of course, you have groundwater velocity changing according to the tides, of course.
Okay.